Hi, good day everyone, welcome to my class. Today we will look into a new topic with the title of rubber. Basically in this chapter, we will look into 6.1, which is natural rubber, and then followed by 6.2 synthetic rubber, or in this case I put SR. 6.3, advantages and disadvantages of natural rubber, have over synthetic rubber, and then followed by 6.4 vulcanization, 6.5 natural rubber latex. And last but not least will be the advantages and disadvantages of natural rubber latex against synthetic dry rubber. So after the lecture, you should be able to explain the polymerization, chemical and physical properties of natural and synthetic rubber, describe the advantages and disadvantages of natural and synthetic rubber, briefly elaborate on the vulcanization, sulfur, and non-sulfur cross-linking. Lastly, briefly state the composition and properties of natural rubber latex. We have looked into many natural polymers previously, such as DNA, RNA, protein, cellulose, starches and so forth. One of the most well-known natural polymers is polyisoprene or natural rubber. The milky sap can be extracted from a tropical tree named Hevea brasiliensis. Let's take a look at its structure. Obviously, polyisoprene comes from an isoprene monomer. We can see that it consists of diene, meaning to say that it has two double bonds in the backbone. It is also a highly amorphous polymer and possesses elastomeric properties. It means that it can be stretched, elastic and viscous. This natural rubber has an odor and sticky. It exhibits transition glass temperature around -70°C. Isoprene monomer is aligned in the polymer backbone, but in nature, it is actually helical or coiled in structure. This helical structure is responsible for its elastic behavior. The Americans in pre-Columbian time used to make rubber as waterproof boots and ball for playing games like basketball, but the boots could only be used in a warm climate, as they will become brittle and crack in cold weather. We mentioned previously, the glass transition temperature for the natural rubber is around -70°C, which in cold weather will be cracked and brittle. Therefore, people in cold places could only use natural rubber for a razor. And this is where the word rubber first initiated. Polyisoprene can possess two isomeric forms, which is cis-1,4-polyisoprene and trans-1,4-polyisoprene. You can see that, in the case of cis polymer, the methylene unit can be found on the same sides, while the trans polymer contains methylene units at the opposite sides. Cis-1,4-polyisoprene can be found in natural rubber, while trans-1,4-polyisoprene can be found in different species, which is gutta-percha. They exhibit different properties. As for cis polymer, its spatial configuration contributes to its high elasticity. Therefore, it is soft, pliable, easily soluble and high refractive force. It is often being used to make vehicle tires. As for trans counterpart, it is commonly crystalline solid at room temperature. Therefore it is tough and really hard. It is used to make golf ball covers. Now, we look at the physical properties of rubber. Rubber is a waterproof polymer. It is also resistant to alkalis and weak acids. It is elastic, tough, impermeable, resistant to electricity and tends to adhere. Therefore it is suitable to make adhesive coating, insulator and molding compound. The rubber displays elastomeric properties, meaning it can recover its shape after being stretched or deformed. All rubber is actually stretchy, due to its entropy. So what is actually entropy? I will let you know shortly. Here we apply the second law of thermodynamics, which states that a system will move from a state of order to a state of disorder. I mentioned about the entropy in the last slide. I'll give you one example. Think of one day you are in your room, watching Korean movie while eating popcorn. You tend to easily make a mess in your room about time. Food, wrappers are everywhere. You are said to be in high entropy, a high degree of disorder. Suddenly your mother comes in, scolding you and asking you to clean up the mess. Here comes the pressure. You are forced to clean the room. You do it slowly, and it seems like forever to clean everything up. When everything is in order, you are said to be in low entropy, low degree of disorder. And after several minutes of nagging, your mother leaves the room. And without hesitant, you jump back to your bed, stop every cleaning that you are doing, and watch your favorite movie again. It is pretty much similar to what happens in rubber molecules. While being unstretched, the molecules are just tangled up in a random mess. It is said to be in a high degree of entropy, similar to your room just now. But while being stretched, the molecules become aligned. They are forced to be in order. Now it is said to be in a low degree of entropy, and low degree of disorder. When the stretch is released, the chains become this disorder again, which snap back to their original size and shape, just like you watching Korean drama again. Synthetic rubber is the artificial elastomer that mimics mostly the properties of natural rubber. It is used as an alternative to natural rubber. Instead of extracting it from the plant, it is synthesized from petroleum byproducts through Ziegler natta polymerization, using a mixture of triethyl aluminium and titanium tetrachloride. It is improvised in many areas and complements the laxness we found in natural rubber. The history of synthetic rubber was started during World War II, where the supply of natural rubber was cut off due to Japanese forces in the South Pacific, and the world needed a new supply of synthetic rubbers. Now, synthetic rubber has a larger market share, and mostly competes with natural rubber in just a few applications, such as in tires. Around 80% of synthetic rubbers are used by the automotive industry. Many variations of synthetic rubber can be prepared from a mixture of monomers or copolymers with various catalysts. Among the early synthetic rubber produced was styrene butadiene rubber, or SBR, or we call it Buna S. Please note that Bu stands for butadiene, Na stands for sodium catalyst, and S stands for styrene. The second example of synthetic rubber is NBR, or nitrile butadiene rubber, or we call Buna N. Similar abbreviation as Buna S, except for N stands for nitrile. We also have polychloroprene, or the trade name is neoprene. Other synthetic rubbers includes thiochyl's butyl rubber and silicon rubber. Some synthetic rubbers are less sensitive to ozone cracking than natural rubber. Natural rubber is sensitive, owing to the double bonds in its chain structure, but some synthetic rubbers do not possess these bonds, so are more resistant to ozone cracking. Both natural rubber and synthetic rubber have high tear resistance, good low temperature flexibility, and high tensile strength. The heat buildup is generally conducted by exposing a rubber sample of a specified size and shape to oscillating compressive stresses. During this process, heat will be generated by the stress. In the case of natural rubber, it produced less heat than its synthetic counterpart. The natural rubber also possesses greater resistance to tearing when hot. Compared to natural rubbers, synthetic rubbers offer many advantages, such as better resistance to aging and weathering, and suitability for use in environments exposed to chemicals, oils and greases, oxygen, ozone and certain chemicals. It is also resilient over a wider temperature range, and other extreme conditions. Here I shared 3 video links related to the preparation of natural rubber, synthetic rubber, and vulcanization process for our next subtopic. This is the next part of our topic. Crosslinking is a way of chemically joining all polymer chains of a piece of rubber into one giant molecule. On your left side, you can see the uncrosslink rubber without any bond attached to its chains. Therefore, once you give an external force to the system, it will eventually deform, and once you remove the stretch, because nothing holds them together, they cannot get back to their original condition. However, if you see on your right, it is a structure of cross-linked polymer. It consists of chemical bonds that attach each one of the polymer chain, and if you introduce an external force, they will move independently and deform, but once the stretch is removed, it will eventually come back to its original positions. This bridge will tie the polymer chain into one specific shape, and the rubber without cross-links, they might deform after being stretched repetitively. Vulcanization is one type of cross-linked process, eventually give you a thermoset elastomers. Once you treat it with chemical and heat, you cannot get back the original starting material. It will permanently become a thermoset product. Vulcanization is the specific curing process of rubber, involving high heat and sulfur. This chemical process, in which polymer molecules are linked to the other chains by atomic bridges composed of sulfur atoms. The end result is that springy rubber molecule become cross-linked, and it will make the material harder, much more durable and more resistant to chemical attack. Due to the strong bond between them, it also makes the surface of material become smoother, and prevent it from sticking to metal or plastic. Heavily cross-linked polymer has strong bonds, with strong forces between chains. Therefore it is insoluble, and infusible thermosetting polymer. The amount of sulfur will determine the hardness and rigidity of the final product. This is one of the papers published by a group of researchers where they studied the effect of vulcanization temperature upon rupture. When they used 120 degrees Celsius, it requires 9 Newton of force to rupture the polymer. By increasing the temperature up to 180 degrees Celsius, they required even up to 13 Newton of force to rupture the polymer. Here we discuss the reason why we need to vulcanize the rubber. The uncured natural rubber is sticky in nature. Therefore it is easily deformed upon heating or warming. Furthermore, due to its glass transition temperature, it easily gets brittle and cracks when cold. So for that, we cannot make a polymer product with good elasticity. The polymer chains in natural rubber can move independently in an irreversible change of shape. These cross-links can form bridges between the polymer chains, and tie the chains together. Upon external force, the chains cannot move independently anymore. As a result, the vulcanized rubber will bounce back to its original position when the stress is released due to the bridge that tied the chains together.